Hi, it's Mr. Forrest back again with another exciting physics video. Anyhow, this is about graphing and some background about graphing that I think is going to be useful. I know you've learned this a bunch of other times. I'll try to go through it quickly to make sure that the way we talk about it here is what's going to apply to physics all year long. So the main thing about graphing is you want to be able to represent data in a way that people can interpret quickly and correctly. So almost always when we make graphs, we're going to make lines or curves as graphs. We're not going to have pie charts, we're not going to have data tables or things like that. Because the goal is to see when you're comparing two or more things, do they have a relationship with each other or do they not have a relationship with each other? And I'll be giving you out something called a graphical method summary that'll help you think about that. It looks something like that. And it's also on my Google Classroom. At any rate, I've got a set of data that I've made here. So I'm going to put this up. And we're going to try to make a graph from it. One of the first things that we need to do is figure out what goes where. So if I want to make a graph, it's a line graph. We're going to have a vertical axis and a horizontal axis. On the vertical axis, you're going to have your dependent variable. And on the horizontal axis, you're going to have your independent variable. One way that helps me think about this is down here when we think about this axis as being the independent variable. Independence is kind of like you making your own decisions, right? So this is what you choose to measure. So these are the things that you're choosing to measure. These, or the dependent variable over here, is sometimes called the responding variable. In other words, when you change this, this follows along. Sometimes it's unclear, and there's some times where we'll purposely choose to switch that up. But the standard convention about graphing is that the dependent variable on this axis, the vertical axis, an independent variable up down here. So with this data set, we're comparing, say, a store that's open could be, I don't know, some small store, number of hours it's open, and the number of customers they've had cumulative for those hours they've been open on, say, 5 different days. So 1 hour, the store had 20 customers. Another day, when the store's open 6 hours, it had 110 customers. And we want to plot that out. So when I think about that, the store owner can choose how many hours the store is open. The number of customers depends on how long he's chosen to have the store open. So this is my dependent variable and this is my independent variable. So I'm going to have time store open and the units are going to be hours. So I'm going to label my axes and put units on there. Over here, I'm going to have number of customers, or I could say customers number. Now you always want to title your graph, and the conventional way to do that is put whatever your y-axis variable is versus your x-axis variable. So I would say customers versus time. And you can put time stores open if you want. So what we've got off the bat is we've picked our variables, dependent and independent. We've labeled them, and we've got a title. So the next thing we need to do is scale things. If you notice, it looks like I've got a lot of data around 1, 2, and 6, and then I've got a big piece of data here at 10. You want to make sure that all your data is included in the graph, and maybe that the graph has a little more room in case you were to collect more data later. So you definitely don't need to label every data point, and you don't necessarily need to label them like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because that makes the graph messy. You want to have enough data points where you know how to plot it, but not so many where it makes it messy and hard to read. A graph should be something you can understand to start off with, at least for many simple graphs within 5 to 10 seconds. Complex graphs, that might take a little bit longer. So what I'm going to do over here, I see that my maximum value over here is 170. So I'm going to max this out at about 200. And if you've got graph paper, you can figure out how to scale it. Don't do weird scales where like every line is 3 or 7 or 5.5 to fill the paper up completely. It's okay if you don't fill the paper up completely. Like I said, it needs to be big enough where you can see the relationship, and something where you maybe got room for some additional data. So I'll put this as 200. 100 would be here, 150, 50, and 0. And we don't always start from 0. I should probably have had that a little further off to the side. So we don't always start from 0, but for many times we will. One of the things you might think about is, well, wait a minute, there's no data around 0. Maybe we should start at 1. I want you to be careful about that, and I want you to be careful about putting breaks in graphs. So someone might want to start somewhere instead of 0. They might do something like this, go like 0, 100, 200, 300, 400, 500, 600 for some sort of data. I don't want you to do that. Or go from 0, have a break in the graph, put 500, then 600, 700, 800. Don't put breaks in graphs because it skews the data. Again, there's times where people will do that, scientists will do that, but not in a beginning physics course and not for what we're going to look at. Because a lot of times what that means is you'll zoom in on a really small piece of data, and it makes you think that the small changes are really important because they're magnified. So again, we don't want breaks in our data, and we want to have consistent scaling. So on this axis, I go up to 10. It seems like 10 should be enough, but I might want to be a little bit bigger than that. So I might go up to 15 just in case I collect more data later on. So I might go by 5. So I'd say 5, 10, 15. And I know that's not using up all the space, but I want you to understand that you don't have to use up all the space. So I'm going to plot some points. I've got 1 and 20. And again, if you've got graph paper, this will look a little bit better. So 1 and 20. Make a nice big point, not just a little dot. 2 and 35. 3 is not there. 4 and 75. And if you're making a graph on a whiteboard like this without a graph background, it's going to be a sketch. It's not going to be perfect. 10 and 170, and notice these don't have to be in order. I don't always have to go from low to high. So 10 and somewhere around 170. And then 6 and 110. So something like that. So if you notice, it's a line right there. It might be a curve. It's a little hard to tell. Might be a line. You're going to want to always put in a line or a curve of best fit. So in this case, I'm going to guess a line of best fit. You might want to use I would recommend using a straight edge when you make something like that. Now the question might be to you, it looks like this might go a little above 0. Should I draw it to 0? Well, the question might be at that point, do you think it makes sense that the graph should trend to 0? So if you're a little bit unsure about that, whether or not you should have a y-intercept or not, right? In other words, an intercept up here or below here. Think about it. So in my mind, it makes sense that if the store never opens, it's open for 0 hours, they would have 0 customers. So even though that wasn't a data point that we collected, I think it can be assumed that there's a data point there, or there would be. So I'm going to do something like this. Again, not perfect. And if you want to make a straight line of best fit, you want some of the points above the line and some of the points below the line. And again, it's going to be an estimate. And when we use something like Blogger Pro or graphical analysis, we'll be able to figure out how good of a fit that is. Now, if you look at this, the top point is below the line and all the other points are a little bit above. So I might question whether or not that's a curve. We'll get into that a little bit later in the course. But right now I'm going to approximate a straight line. One of the other things you may want to do is make an equation from that line or a mathematical model. So that's something, again, that I think is pretty important because it allows us to make predictions. So maybe we had a store open 50 hours in a week. We could predict how many customers there would be from this. So in this case, what I'm going to do is I'm going to take the slope of this graph. The slope is equal to the change, and that's symbolized by a triangle. That means change. And the y-axis values, that's number of customers, divided by the change, and again, that's that triangle, in time. So when you want to do that, you want to pick two data points that are easy for you to use to get the slope. So I'm going to pick one here as 0, 0, because that makes sense to me. The other one, I'm going to pick here at 10. Oh, I didn't do that very well. There's 10 hours and 170, and that should be like, that's okay, I guess. It's right there. I'm going to pick 10, like right here. Now, if you notice, though, I've got a data point already at 10, and it says 170. So why would I just use that? I wouldn't use that, because that's one data point, and it's not the best representation of the trend, which is what we're looking for. So what I would do is I'd go up here, I'd say that's that point, and I go over, and in my mind, the line would cross 10 hours with about 180 customers. Okay, so that's the point that I would use from the line, not from the data points themselves. So in this case, the slope, I'm going to call this point 1 and this point 2. So my point 2 number of customers is 180 minus 0 and the time is 10 minus 0 hours. So my slope is equal to 180 over 10, and that's 18, and the units for this would be customers per hour. Customers for every 1 hour of time that the store is open. So that's the slope of that graph. How does that help me? Well, now what I can end up doing is I can make an equation which is going to allow me to make a prediction. And that would be true whether or not there was a y-intercept. So the general formula for a straight line is y is equal mx plus b, if you remember back from algebra. So y is your y-axis variable. In this case, it's customers. M is the slope, which we just figured out is 18 customers per hour. X happens to be an x-axis variable, which is down here. In this case, that's the time the store is open. And a b, that value would be y-intercept. In this case, we have no y-intercept. So although this is a general equation, I want to turn it into a specific equation for this set of data. So I'm going to use the variables that I've got over here. So I'm going to say customers. I'm just going to have that as a C. Actually, I'll do write it out a little more first, and then I'll make it only a letter C. Slope, 18 customers per hour, multiplied by time, plus 0, because my y-intercept 0 customers. If you have a 0 y-intercept, it might be okay to leave that off. So I would say this turns into C equals 18 customers per hour times time. And that would be my equation for this graph. That way, if somebody tells me, hey, we want your store to be open 40 hours a week this week, I could just take 40 hours times 18 customers per hour, and I could turn that into, let's see, that's 720 customers. That's how many I would expect. And that would allow me to predict how many materials to order, what to purchase, things like that for inventory. So those are the general rules of graphing: labeling, scaling, dependent and independent variables, not zooming in too much on a graph by using graph breaks and things like that, how to get the slope from a graph, and then how to get a general straight line equation from a graph. So I hope that helps us out as we go through the rest of the school year.